Hello, everyone. We are here for the fourth webinar of Emerald's project. We are admitting people, and the webinar will start in a few. So let's wait for 1 minute, and then we start. Thank you. So just a few recommendations at the beginning. So first of all, welcome everyone to this fourth webinar of Emerald's project. We today talk about data processing and analytics services. We have a very interesting agenda. So we start with the project overview and status of the project itself from the technical coordinator, Yannis Theodoridis, and the project coordinator, Konstantinos Dafloulas. Then we start talking about privacy. So with the speech from George Theodoropoulos on privacy-aware mobility data ingestion. Then we will have the Professor Christos Doulkeridis on extreme scale parallel distance joints. And then we talk about mobility data fusion and management with Baher Salehi, and about urban micro-mobility demand forecasting from Antonis Diorvas. Then we will have the last speech from Anahi Wachasenbach for explainable and federated crowd density forecast. I apologize in advance if I don't say the name correctly, but I want to welcome all the speakers today that gave their availability to stay here with you and talk about these interesting projects today during this interesting webinar. We will talk all together in a proper session. We will have the panel discussion at the end. So I invite everyone that is attending this webinar to post their question in the Q&A box below on your screen. And I just want to give you a few advice. So the questions are kept there. The webinar is recorded and will be available afterwards on the Emerald website and YouTube channel. And also the slides will be shared after the webinar. So I give the floor to the first panelist. So please, Yannis, the floor is yours. Thank you.
Is it okay now?
Yes, Yannis, we can hear you now. Yep.
Okay. Now I share my screen. Is it okay? Good.
Yes.
Yeah, perfect. Thank you, Yannis. Go ahead.
Thank you, Maria Letizia. Also from my side, welcome to our webinar. This is the fourth webinar of the Emeralds project about extreme scalable mobility data analytics as a service. And this is just a technical introduction and overview of what is going to follow. So I will not spend much of the time. Let me just position our project in the academic, let's say, framework. We are talking about big data, big mobility data, and urban environment is exactly a framework that provides, a domain that provides such kind of big data. We talk about high volume, high velocity, a lot of streaming data, high variety, from latitude and longitude coordinates to weather data, high complexity, and of course, something that will be touched in this webinar, sensitive data. It is privacy is an issue here, and of course, heterogeneity. All these dimensions are important to be covered in a project like this, and we are doing exactly this stuff here. Just at a glance, what is the project technically? It is to develop, the goal of the project is to develop a state-of-the-art mobility analytics as a service ecosystem for urban environment, which will be easy to deploy, consisting of advanced services, consuming extreme scale data, both historical and real time, using AI and machine learning driven models, and also, of course, touching the computing continuum from the edge to the fog to the cloud. And so far, we are at the beginning of the third year of the project. We have already developed some very, very nice results. According to our opinion, a list of them, a selected list of them will be presented today, not only from the data processing and analytics point of view, but also the framework, the data infrastructure development framework. So to position our webinar, our today's webinar, we will present some highlights of the first group, the data processing and analytics services, and there will be a follow-up webinar. Maria Letizia will tell you the details in the end, during the conclusions, covering the data infrastructure development framework, the second group of our advances, where we demonstrate, validate all these results developed during all these months in three pilot cities. The Hague, Netherlands, is the first one. The idea is that the goal there is to improve safety and security measures during some events. And as you understand, during events, everything changes in the normal life of a city. We have overcrowding places. We have some extra risks to be addressed. The second pilot city is on Rotterdam, where the idea here is to reduce the traffic congestion and improve the traffic flow. What the transportation and domain experts call forecast as a service, and have advanced traffic management systems. And the third pilot is in Riga, Latvia, where we have efficient public transportation as the goal, optimize routes, calculate the movement of citizens, reduce the carbon fingerprint. The project, as I said earlier, is now beginning its third year. Actually, it started January 23 and has already reached the 3 of the 5 milestones up to month 24, which was last December. What we have done this month, we have already designed our reference architecture. We have the preliminary implementation of the Emeralds ecosystem, which will be presented in the forthcoming webinar. We have developed already some state-of-the-art service tools. Some highlights will be presented today. We have mapped these tools with the needs of the use cases, and through this matching, we have made a preliminary assessment. The project is Horizon Europe, under the Horizon Europe program. In particular, it is a data call, research innovation action. As I said, it started January 23 and it will be concluded December 25, 36 months. And this is the consortium consisting of 19 partners from 10 different countries. This is from my side. As I said, it is a brief just to give the idea of what's going to follow. If Konstantinos has something to add, please, Konstantinos. Otherwise, back to Maria Letizia.
Yes, thanks, Yannis. for providing these useful details of the project. Of course, yes, you know, the Emerald overall vision is to targets to design, develop, and create an urban data-oriented mobility analytics as a service, the so-called Emeralds that we have in the project. So these toolsets targets to enable the stakeholders of the whole urban mobility ecosystem and general infrastructure systems to collect and manage spatiotemporal data of high volume and high velocity, as Yannis described, and analyze them both online and offline. Of course, we have some nice results here with AI and ML algorithms that help us to visualize the results in interactive dashboards. And I'm looking forward to hearing the results in this webinar under a more technical perspective. So that's all from my side.
Good. Maria Letizia, back to you.
Thank you very much to both of you. This is very interesting, let's say, introduction with the presentation of the project. But now we'll go to George Theodoropoulos, who will talk about privacy and privacy-aware aspect in mobility data ingestion. So, George, the floor is yours.
Thank you, Maria Letizia. Hi, everyone. Dear attendees, it's nice to have you all here with us. Let me share. Okay, so thanks again, Maria Letizia. Thanks for trying to pronounce our Greek names. It's a great honor for us. So let's just jump right into the agenda. As you see, we have some points here to discuss. The overall, of course, title of the presentation is Privacy-Aware Mobility Data Ingestion. The areas that we'll focus today, of course, we'll talk about the motivation, why we plan and why we do these things, why we try to safeguard user privacy, and why it's important today. We're gonna discuss about the role of edge computing. Then we're gonna go one by one and see some privacy attacks and how these attacks can be used to safeguard user mobility. We're gonna see 3 specific attacks today, just for a frame of reference. And then we're gonna jump to the unified knowledge base that is what we propose to the community in order to make all these attacks and all these de-anonymization and privacy enhancement steps more efficient. Then we're gonna check the internal architecture of our offerings, and then we're gonna have some preliminary results. So I guess I should jump right into to my first slide here, which is about motivation. So as you can see, as we all know, in today's world, of course, everyone is interconnected. We use smartphones, we use micro-mobility services, we use smart buses, and all these movements are being in one way or another tracked and kept in central databases mostly. This can be good and bad. On the one hand, understanding people's movements can be beneficial for designing more efficient urban networks. But on the other hand, most people, I would say, really should or are already valuing their privacy quite heavily. So it's important that we don't really sacrifice people's privacy and people's fundamental right to not be surveilled. By finding ways to actually make analytics easier and possible without giving out information that people might think is sensitive. So the important thing here is we need to keep in mind that all the information that we need, as researchers need and as analysts need, always correspond to specific people's movements, and we need to be sensitive and we need to be aligned with the value system that we need to hold. So you can see here just some illustrations and some examples of some snapshots from that basically correspond to people's movements, either from taxis in New York City or, for example, from GeoLife datasets, which is the one, if not the biggest mobility, urban mobility dataset primarily from cities in China. So let's jump to the role of edge computing and why edge computing specifically is important in the realm of privacy enhancement and people and the privacy discussion in general. So the edge computing, of course, as we all know, is using embedded systems and low resource systems that are deployed in the field to actually ingest and process data in situ. So without having data leave the field and being transferred into central databases as it normally is, as it's normally the case. So the role of edge computing is very important in the realm of privacy enhancement technologies and privacy and insurance for people's movements, because it acts basically as an intermediary. So as you can see in the left-hand side, you can see a diagram, a very brief diagram about how people's movements can be processed and stored using the edge as an intermediary. This way, data is processed on the edge devices and is then transferred to a centralized storage. On the other hand, if there's no edge, data is fed directly to the centralized storage infrastructure, which means that any sensitive information that might be hidden inside these data points remains available to the people that have access to these centralized resources. This is a potential hazard because, as we all know, the more we keep sensitive data away from prying eyes, in a better spot we are. So let's jump to the idea of de-anonymization attacks. This idea is a central part of privacy preserving privacy preservation for mobility data specifically. When we talk about de-anonymization attacks, we talk about ways of using available data to backtrack essentially and attempt to find specific mobility patterns of people that correspond to their specific situation. So for example, if we know that someone lives in place X and then works in place Y, if we can see that if we can find in a dataset, in an anonymized dataset, mind you, we don't talk about non-anonymized datasets because that's of course out of the question. In an anonymized dataset, if we can find someone that is very frequently traveling between those two locations, we can extrapolate that it's highly likely that this person is the one that we're looking for. So this can be done in multiple ways. This home and work idea is just one of the many that have been proposed. Today, we're gonna talk about three specific types of attacks. This is classified as an attack, but of course, we can use these attacks to actually sanitize and ensure that sanitize our datasets and ensure that every potentially sensitive piece of information that could lead to these de-anonymization attacks can be removed, and thus the whole dataset becomes safer. So let's start with the first privacy attack, which is the one that I used previously, which is called home and work. The goal of this attack is, of course, to identify specific people through their home and work places. So, for example, here, if you can see the map, which is an illustrative way of viewing things, and I think it makes it much easier in this case, you can see that A and B, red and green, actually share the two most frequent places that they visit. So, of course, through their trajectories and through their trips, we can find the two most visited places for these specific users. And in this case, those two users, A and B, share these places. This means that essentially they become safer because we cannot really know if a person that works in these and works and lives in these two places is either A or B. So the identification risk is actually 0.5%, so 50% instead of 100%, because we have two users. On the other hand, for C and D, it's the opposite. So for C and D, we don't know, we know specifically the work and home places, the two most frequent places that they visit. So if we have this information somehow, we have obtained this information, we can really easily de-anonymize these people and find out who these people are in our dataset. Then we go to the next attack, which is called the unique location attack. This unique location attack is based on the fact that specific users visit specific unique set of locations. So again, if we look at the map, we can see that green B visits 3 specific locations, two of which B shares with D, but one that is not shared with anybody. This fact, alongside the fact that everybody else actually A and C share a lot of locations, means that B and D can be anonymized in this sense. So they have 100% risk of anonymization, and C and A have 50% risk of de-anonymization. Then we go to the location frequency attack. This attack is kind of similar with the unique location attack, but in this case, we really try to identify users based on the frequency that they visit specific places. So as you can see again, for example, in the place on the top left-hand side, we can see that blue and red visit this place and every other place with the same frequency, and thus can be harder to de-anonymize. And that's why the risk of anonymization is halved. On the other hand, again, B and D are really easily de-anonymized in this sense, and that's why they have 100% and basically one point for de-anonymization potential. So our approach in this field is the following. We propose a very comprehensive set of steps that leads to the construction of a unified knowledge base. We start by segmented trajectories, finding out the origin and destination of these trajectories, and then creating a unified knowledge base that can be used to execute all of the aforementioned attacks. This way, through the construction of such a knowledge base, we can actually really speed up the process of execution and provide results in an extremely more efficient and fast runtime when compared to other existing state-of-the-art implementations. Of course, in the latter stages, we can sanitize and produce a dataset that is safer than the original. This is a snapshot of the internal architecture of our approach. You can see that we start with an input dataset with preprocess. During the preprocessing steps, we segment, we calculate the origin and destination of each trajectory, and then we construct the knowledge base, which you can see on the bottom left-hand side. And then through the execution of the attacks, we can actually get an identification risk data frame that can then lead to a sanitized dataset. So regarding the results, our approach uses Rust and Polars, whereas the current state of the art, as far as we are aware of, which is based on an open source library called Scikit Mobility, uses Python and Pandas. Our approach is much faster than the Python and Scikit Mobility approach that is currently used widely. Its speed up is more than 5x based on our experiments. We propose the unified knowledge base, as mentioned before. We have implemented four specific attacks. And of course, we have added the process of sanitizing the dataset by removing the trajectories that are the most prone to de-anonymization. And I think that's pretty much it from my side.
That's great, George. Thank you very much for your speech and for your presentation.
Thank you.
So now it's time for Christos Doulkeridis to talk about extreme scale parallel distance joins. Please, Christos, the floor is yours.
Yes, thank you, Maria Letizia. I think you can see my screen now.
Yeah, very well. Yeah.
Thank you very much. So I will talk to you about extreme scale processing of parallel distance joins. This is work that we have carried out in the University of Piraeus. So let me start by trying to introduce the problem. So The idea is that if we have two sets of spatial objects, S and R, the problem is to retrieve all pairs of such objects such that these pairs are within distance epsilon. So epsilon is a user-specified threshold, so we're interested in finding objects that are close to each other. So in this tiny example that you can see here, we have these two sets of objects, the dark circles and the white colored circles, and we want practically to find all pairs that are within distance epsilon. So these red circles correspond to a radius of epsilon, and the output of this specific query for this simple data set would be, for example, R1 and S1 because they are within distance epsilon, and similarly R3 with S2 and R3 with S3. So this is practically the spatial distance join problem, and it has many applications in urban planning, in cartography, but also in other sciences such as neuroscience. And of course, when you have a lot of data, so you have large scale data sets, the challenge is to perform this in a parallel way, to process this query in a parallel way in order to achieve scalability. So let's see how existing solutions target this problem. So the idea is that with the existing solutions, they try to partition the data into separate partitions. Here in this example, we have just two partitions to illustrate the idea. And practically all the objects that are enclosed into the first partition are assigned to one processing unit, to one computer, and all objects that belong to the other partition are assigned to another processing unit. And then in order to compute the correct result and be able to identify all pairs of objects, we need to replicate some data objects from one of the two datasets to the neighboring partitions that are within distance epsilon. So in this example, if we choose to replicate the white colored dataset, then S3 and S4 need to be replicated to the other processing unit so that we don't miss any pairs. For example, now, after having replicated S3 from the left partition to the right one, R3 and S3, this pair can be identified by the processing unit 2. So this is practically this idea of universal replication of one of the two datasets. This is the basis for an algorithm which is called partition-based spatial merge join algorithm, or PBSM, which is an algorithm that has been proposed many years ago, but it produces a correct and duplicate-free result. And also, until this day, it is widely used by many state-of-the-art systems and big data frameworks. For example, if you have heard of Apache Sedona or Beast or Magellan or Location Spark, all these are big data frameworks that process spatial data, and they rely on this algorithm. Now, our key observation is that this algorithm, as I said, universally selects one dataset for replication, and this can lead to suboptimal performance. When does this happen? This happens especially in the case of skewed datasets with varying density. And let me try to explain how this happens. So here in this example, we have a simple example again with two datasets, but as you can see, they have varying density. That means the dark colored points, they are sparse in the space, whereas the white colored points, they are really dense. So in this case, if we again try to partition the space into two partitions, you can understand that there will be a lot of replication of white colored points between the two partitions. So we'll have many replicated points. And if you think that, okay, maybe I could choose to replicate the dark colored points, the problem wouldn't be solved because there might be other areas in the space where the dark colored dataset is dense and the white colored dataset is sparse. So the takeaway here is that datasets with varying density can lead to excessive replication. In the chart, you can see PBSM, which is the white colored bars. And you can see on the y-axis the replication, how many times more replication it requires in comparison to the dark colored bar, which is our adaptive replication approach that I will describe about. And this happens for many different dataset combinations. So you can see that it needs like 15 or to 75 times more replication of data. And as you can understand, this has a negative effect on query processing performance. So motivated by this observation, what we propose is an approach for adaptive replication between partitions. In this example, the partitions now are cells of, as you can see, A, B, C, D. We have 4 cells. And the idea is that we would like to make local decisions about replication. So, for example, we would like to replicate R points between A and B, but S points between B and C. So dark colored and white colored points according to the different areas of the space. And the challenge is how to do that and at the same time guarantee that we can find the correct result when you process this in parallel, and also you don't end up having duplicate results. So the same pair of objects being reported by 2 different cells. And the way we do that, we introduce an abstraction, a graph-based abstraction, which is called the graph of agreements. So this graph, practically, each vertex of the graph represents one of the partitions, one of the cells, and you can see that there are edges with different color, dark or white, according to the type of object that is being replicated between the 2 cells. And in the paper, you can see the details below. In the paper, we explain the technical part, which is how can we obtain such a graph that guarantees correctness and duplicate-free results. And when you have this, then you can perform adaptive replication. So you can, for example, as I said, replicate R points between A and B and S points between B and C and still get the correct result. So this was the technical challenging part of the work. And if you are interested in these details, you can have a look at our paper, which will be presented in ADBT in March in Barcelona. Just to give you an idea about how, after having computed this graph, how you can implement this spatial join in parallel in Apache Spark, you can check this example here. We have 4 worker nodes. The worker nodes are those that on which the data is stored, and we want to compute the join. There is a computer which is a driver of the cluster of worker nodes, and our approach works in the following steps. In the first step, we perform a sampling, so we collect a small sample of data from all servers, and based on this sample on the driver, we can compute the graph of agreements. So we create this graph and we make the decisions about from where to replicate which type of objects. Then this graph of agreements is sent to all workers, and as a following step, data is being shuffled, it's being moved among worker nodes and replicated according to the graph of agreements. So as you can see in the figure now, each worker is responsible for a specific partition of the space and can perform the join in that partition independently from the other workers and in parallel. And then the join processing takes place and the results are reported. So this is a very high level description of how the algorithm works in a parallel way. So some results very, very fast, just to give you an idea. So practically our variants of our adaptive replication algorithm are the 2 dark colored bars that you see in these 2 charts. And the main takeaway message here is that we have less data that needs to be remotely sent between nodes. That this is shown on the left graph. Whereas on the right graph, you can see that our approaches need much less execution time in order to perform the join. And we compare our approach against Apache Sedona, which is widely used in practice, and also against some baseline implementations of the PBSM algorithm that I described earlier. So you can see you can have very nice results. And also when we increase the number of nodes, we also achieve scalability because the processing time is less. So to summarize, in this work we have introduced a parallel distance join algorithm that improves the state of the art. And the basic idea is to use adaptive replication instead of replicating universally one dataset. And we can easily understand that this is better for real datasets which have varying density and not, for example, uniform distribution. We have proposed the correct and duplicate-free algorithm and its implementation in Apache Spark. And the results show that using our approach, one can achieve much fewer replicated data objects, about 1 order of magnitude less, and you can have much faster query execution, for example, up to 5 times faster than Apache Sedona. And this concludes my talk. Thank you very much.
So thank you very much, Christos. And you gave an appointment also for March. So this is the opportunity to remind everyone to follow Emeralds, because we are present in a lot of events, and we talk about our results and our projects everywhere. So please keep updated. Stay updated on the news, following our newsletter, our website, and our social media channels. So thank you, Christos, again. I give the floor now to Bahar Salehi. She's talking about mobility data fusion and management. So the floor is yours. Okay, and we can see your slide. Thank you.
Yeah, thank you. Hello, everyone. My name is Bahar Salehi from University of Brussels. And today I will present our work on mobility data fusion and management in the Emeralds project. Here we will first go through the task description and the motivation, talking about some of the key challenges in the working with mobility data and services we will develop in the Emeralds project to address these challenges. And then we will go through the workflow of each service and the results from our experiences. Okay, as we know, mobility data is a key resource these days for understanding and optimizing urban traffic systems. This data is collected from diverse sources such as buses, vehicles, loop detectors, and comes in different formats like spatial temporal data, GTFS feeds. And actually in the pictures you can see as an example, we highlight here Brussels City as one of our case studies, where you can see two mobility data sets that collected from this area. Bus network data and scooter data as two examples. And also in other urban areas, in other case studies, we can collect different and similar data sets, mobility data sets that provide a great opportunity to study mobility. But collecting these data sets and accessing a large amount of data is just the beginning step. To make this data usable, we must first manage and process this effectively. So before utilizing this collected mobility data for tasks like predictions or analyzing, we need to address these key challenges. Challenges like high data generation rates, which is our first challenge we're covering here. And it happened caused by continuous collection of data in different types and different modes, which make a storage, retrieval, and a process of data, real-time data or historical data difficult. And also we are facing missing values in the mobility data frequently, which is the other challenges we are addressing here. And this gap in the collected data often caused by sensor failure or communication issues, which reduce the data quality, data resolution for the next tasks. In the Emeralds project, we tackle these challenges through the following approaches. First, mobility data compression. We utilizing lossless compression techniques to reduce the size of the collected data while preserving the key characteristic of the data and ensure the efficiency of storage of data and scalable management. And the next service we provide here is missing data estimation. We develop AI-based estimation model to fill the missing value gaps, the gaps in the collected data, and improve data completeness for further analyzing. Okay, let's start with our data compression workflow, the first service, and our design workflow for that. For compression task, we built a mobility leg to handle larger scale mobility data. In this system, raw data is compressed by lossless techniques and stored in packet files. Packet is an optimized storage format to reduce data size while preserving all essential information, which make it completely suitable for our needs. And also for querying and analyzing this compressed data, we integrate DuckDB in the mobility leg for storing the compressed data. And this setup lets us to retrieve large data sets quickly, which is usable even for real-time analyzing. In the figure in the right, you can see a query example of the compressed data from DuckDB. Here in this example, we show a query that's querying the number of vehicles delayed by more than 5 minutes. We applied our compress tool on the Riga use case in Emeralds. And this use case actually focused on, this dataset focused on public transportation. On the left, you can see the map of public transportation stops and bus routes of the Riga. This network is quite huge, includes 5 tram routes, about 50 bus routes, covering millions of kilometers and millions of passengers per year, showing the high rate of high sampling rate of these datasets, about 2 gigabyte GTFS per day. So by using our mobility leg compression, we achieved a significant reduction on this data. The right plot shows the size of the compressed data for a week compared with the actual size of the raw data, which shows the really significant reduction. This compression tool can be used now by calling a Python API. On the bottom left figure, you can see an example for how it uses API to extract daily position data, for example. I'm so sorry. And this example try to extract daily position data and as a single pi-arrow table or convert them to a Pinda data frame. Here I just wanted to show get the idea what would be the compressed data in these 2 figures. The first one, the first data, the compressed data that all already available in Evident platform shows the snapshot shows a data sample and what information in the compressed data. For example, you can see the bus information. And the second one, you can see in the snapshot the size of 1 day packet file per actually break per hour. So that was for the first service we provided and successfully applied on a dataset. And for the second service, the missing data estimation, let us start with the designed workflow. In the traffic networks, in the traffic road networks, spatial temporal data such as average speed or average flow is collected over time by different methods. For example, in the example I provided here, the data collected by a sensor allocated on the network. The collected spatial temporal data, which is generally come with high rate of missing values, first pass through a pre-processing step to clean. And after this pre-processing step, vary depend on the type of the network. For example, if the data comes from highways or public transportation networks. And then the clean data is fed to our design deep neural network model, which capture a special correlation between neighboring road segments and temporal patterns in traffic time series to estimate the missing values. We applied this estimator tool to the Rotterdam Highway dataset, one of the Emerald's use case. This dataset contains speed and flow data from about 200 loop detectors across the highway network, which collected the data over 1 year. In the left figure, you can see the location of these detectors on the Rotterdam Highway map. And each detector records time series data at a 1 minute interval, capturing traffic patterns, which, as I said, often have missing data. In this slide, you can see the input and output of our estimator tool for the Rotterdam dataset. The left heat map shows a spatial temporal input, and the right heat map shows the estimated interpolated results. Traffic counters are, or loop detectors are on y-axis, and the time series, the recorded time series per each collector is represented on the x-axis. Hotter colors indicates higher speeds recorded by the detectors, and the missing data highlighted by red. The deep model extracts the spatial and temporal patterns in the input data and use this to fill the gaps and improve the data resolutions for the next tasks. We also applied our estimator tool on several real-world datasets, including open source PEMS dataset, which is one of the most famous open source datasets in the field from California, and Brussels bus line datasets generated by our lab, and Thessaloniki urban area. During designing our tool, we used these datasets to test several estimation models with different configuration to achieve better results. And the goal was to minimize the error of the estimated values. And you can see actually part of the reported values in this way, which actually published already. So I think that's from my side, which I tried to describe the two services we designed for challenges and applied on the datasets.
Thank you very much, Bahar. And so we are a little bit behind in time, but we have still two important speech. So the next one is from Antonis Ziorfas, who is talking about urban micromobility demand forecasting. So Antonis, the floor is yours. Thank you.
Thank you, Maria Letizia. So I will try to speed things up in order to recover the, let's say, quote unquote, lost time. We will start with a brief outline of our agenda. We will begin with a gentle introduction to the mobility as a service ecosystem, and more specifically, the shared mobility, which is our main objective. We will discuss the motivation and the objectives of
Sorry,
our.
Antonis, I don't mean to interrupt you, but I don't see your slide.
Okay, sorry, maybe we had a small interruption. Is everything better now?
Yeah, perfect. Thank you. Sorry again.
Okay, sorry for that. So, as I was saying, this is our agenda. We will begin with motivation and the objectives of our problem, which is shared mobility demand forecasting, mainly the what and whys, and address some of the key challenges we encountered during our work. And we will slowly move towards more technical stuff like the Emeralds approach and the proposed workflow. We will also present our experimental setup and a preliminary study along with the results as well, and finish off with a dashboard, sort of a demo that we created in order to help us visualize the results. So mobility as a service actually integrates different types of transport options, including public and private, into a single platform, allowing users to book, pay, and plan their transport easier and in a more unified way. Shared mobility is actually a subcategory of that. That includes the transportation services that enable shared use instead of individuals. With urbanization rising, we need all the more sustainable mobility and flexible transport solutions. And why is that? Because we need to reduce congestion and manage traffic in urban environments, lower the carbon dioxide emissions, and optimize resources. Users, as we said, there is a growing demand in accurate predictions and vehicle availabilities and waiting times. And that provides a challenge for the service providers, which is fleet management, demand prediction, and stuff like that. So what we do to tackle that, we leverage the available data and build and train machine learning models for accurate predictions on the shared mobility demand services to enhance and provide an easier solution for the above hurdles like fleet distributions, as we said. During our work, we encountered a number of challenges, but the main was the data skewness. And more specifically, we discovered there is an imbalanced demand across time and location, meaning that there was a high variation in traffic patterns between the different city districts and between peak and off-peak hours in the same city district. And you can see these findings in the time series plot on the bottom right side of a sample district in Netherlands, mainly the Rotterdam Centrum. So we propose the Emerald workflow, which uses GPS traces of shared mobility vehicles, mainly bicycles and scooters, across the city of Netherlands. And what we're trying to do is to predict the shared mobility demand at different future horizons, more specifically in 5, 15, 30, and 60 minutes. And the whole workflow can be split in 3 main components: the data ingestion pipeline, the data preprocessing, and the model training and evaluation. Beginning with the ingestion part, what we do is we make a request to an API in order to retrieve the data. This API contains shared mobility vehicles in the Netherlands, and it refreshes the data with in a stream way at every 60 seconds. So we receive the response, and along with the associated map data, in this case, we use an example map of the Netherlands. We perform a filtering and keep only the relevant traces that are inside the our area of interest. In this case, it's the Rotterdam city, as you can see here on the bottom right-hand side. So the remaining traces of the GPS are then aggregated by the region. Each city, as an introduction, can be split in many districts. So we actually leverage this information and aggregate them by region to construct density estimates. This can be visualized with the colored heat map, let's say, in the left side. And these results are then stored in an SQL database in order to keep them for later use. So let's say we are trying to predict the demand in a specific district. We obviously don't need the data from the whole city because scooters are more likely to come from neighboring districts rather far away. So what we did is we created an adjacency matrix to speed the data retrieval and incorporate spatial knowledge, and as a result perform localized training on a specific district. Moving on, we also performed some feature extraction processes to capture different type of information. Namely, we created some time-related features to capture the temporal patterns and seasonalities. We use the lag features to get insights into past values and identify potential trends and past dependencies. We are also incorporating some rolling features to smooth out the noise and highlight underlying trends. And finally, the exponential moving features incorporate decaying knowledge as we move towards past observations, beginning from the most present. Another thing to note here is that we also perform some encoding to the actually the value we are trying to predict, which is the demand, I remind you. And instead of predicting the actual value, we can split and categorize them into sample bins. In this case, we use an example of 3 different categories representing low, medium, and high traffic, and trying to predict this class instead of the actual value. So we can actually have 2 different approaches for the same problem. Moving on to our experimental study, a small recap. What we're trying to do is we are trying to predict the demands for a given city district, multiple future horizons, and how we will do that through a regressor or a classifier, respectively, to predict the demand values or the demand levels. To do that, we leverage the dataset we described earlier with minute-wise density data from 2 major cities in the Netherlands, the Rotterdam and Amsterdam. And why we do that is because Rotterdam, as you remember, is a pilot city in the project. So the model of choice is XGBoost. It's a boosting algorithm, which is widely trusted in both industry and the scientific domains. It's really fast, so it will potentially have how do we say, sorry, it can process these large data sets like ours. It's very easy to use, and it can learn from its mistakes, improving predictions consistently, leading to more accurate results. This is our experimental results. We chose 2 major key metrics. For the classifier, it's the accuracy, and the regressor, you can see the error here is a mean absolute error. The preprocessing and the feature extraction we perform appear to be very robust, since the performance of both variations seems pretty high and consistent. However, as you may notice, in the classifier, the the districts that we trained the classifier on were less than the ones from the regressor. And it's because the classifiers had an inherent limitation that did not allow training on all districts. And last but not least, this is a demo dashboard that we created. It has a long way to go, but it can actually help us visualize our results in a more user-friendly way and provide condensed information in a single pane. And I believe that's it from my side as well.
Oh, thank you very much, Antonis.
I was trying to be fast enough, but as much as informative.
You were perfect. Thank you very much for your presentation.
You're welcome.
Yeah.
Pleasure is mine.
And so now we have the last speech from Anna Watzenegger. She is talking about explainable and federated crowd density forecasts. So welcome, Anna. So the floor is yours.
Thank you.
Yeah, thank you.
So I think you can already see my slides.
Actually, not yet.
Not yet?
No.
I try again. Now you should be able to see it.
Yeah, perfect. Thank you very
Amazing.
much, Anna. Go ahead.
Perfect. Yeah. So, hi, everybody. Thank you that you take the time to listen to this presentation. What I would like to show today is our work regarding explainability of the models that we are training for mobility use cases. We are also addressing the models that are federated to make sure that the data privacy is also ensured. So explainable crowd density prediction, what we are trying to do here is to forecast the hourly values of the next 7 to 11 days. And what we would like to say is the exact number of or estimated number of visitors that we might expect in Scheveningen area. And also we would like to predict the crowd density patterns to ensure that we can help the crowd management systems for their resource availability planning and other measures that they need to take. We also would like to leverage the federated learning techniques to ensure that the data providers have the data on their own side and they do not need to share the private information, and they can still manage to use the advantage of using other data sets as well as an improved and more robust model. So what you see here on the left side, you see the monthly density values of the Scheveningen area in different regions. And what we basically do is to we try to understand which regions are neighbors and which regions might basically affect each other's density. And therefore, we use this geographical information to create a model that can estimate the number of visitors for that specific region on an hourly basis for the next 7 to 11 days. How we do this, as you can see here, we have in a specific time series. This is already normalized, and we are using on the right side, you see the actual value of the visitor number, and on the left side, you see the normalized value of the temperature in a specific month. So for example, here we have July. And what we do is to take the previous week of the crowd density and also the next week marked with green of the value of the temperature. And we try to predict how many number of visitors we might expect for a specific sub-region that you can see here. So I hope that was clear. And as an example, what I would like to show is our approach for these 3 regions that are neighbors to each other: Boulevard Mieden, Strand Süd, and also Boulevard Süd. And we already gave these regions a code, and we look at their previous crowd density data, as well as the weather data that we have, and we train our federated learning models. For this purpose, since we have different sort of data, we are using the vertical federated learning. It's not the horizontal federated learning. And the vertical federated learning model that we have, they all have their own isolated encoders. That means each of the regions, they have their own model, local model, and they share the embeddings with each other to ensure that they get a federated model only applicable for their own region. So as you can see here, the weights are basically, the embeddings are communicated with each other, and then using these embeddings, a new model is trained, and the weights are back propagated to create a more general encoder. And the right side, what you can see is that using this approach, we managed to reduce the average loss for evaluation, comparing the red line, which is the isolated losses, and also the blue line, which is the federated validation loss, which is much lower than the isolated losses. And we also look at the lower plot, which is the topper one has the geographical graph, and the lower one does not have the geographical graph. And as you can see, the topper one basically goes down much more when it is federated, when we include this geographical information of the neighbors. For the explainability part, what we do is that we take the models and we try to explain the decision of the models using the SHAP value. For the federated models, it's a little bit tricky because we are not allowed to have access to all of the trained data set. So what we do here is to look at a centric model, which is trained on all the regions. And here on the upper side, you see the exact numbers and the actual data that we have for the previous summer. And the lower one is the predicted summer expected crowd density by our models. And here you can see how the model was performing. So we have the mean average percentage error, which is at 14%, 14.5. We have the R-squared score, which is at over 0.5, which is also good. And we have the root mean squared error, which is at 0.44. So the values are more or less good. We still have the challenge to detect these red zones. The red areas are the categorized risk that we have to tell us when do we expect specific density, specific visitor numbers higher than what we consider as non-risk number. And we need to also increase this. And for that, we are trying to engineer more features, such as creating more weights for specific days, and also creating more weights on the temperature data, the weather data, including the temperature. And we are also looking to see how reliable the model is by considering the explanations. And on the right side, you can see the explanations provided by SHAP. If you're familiar with SHAP, is Shapely Additive Explanations. And what we can see here is that for each value of each of the features, we get a Shapely value. And basically regarding the colors, the higher that value is shown with, let's say, warmer color, and the lower that value is shown with the colder color. And if it falls basically on this side of the plot, which is basically a positive Shapely value, that means it most likely increases the next regression value that the model would predict. And if it falls on the left side of the plot, it will most likely decrease the next value that the model would predict. And here we can see that the model is mostly and largely focusing on the previous hour of the number of visitors, which makes sense, the hour of the day, and also it's looking at the occupancy of a specific parkings. If these parkings are full, of course, it makes more sense for the model to look at those. It's also looking at the daily maximum temperature and also precipitation rate as well. We are also trying to ease these explanations by just looking at a weekly value and trying to consider a rule-based explanations to ensure more understandability of the explanation outputs. This is our group who are working on this project together, and I'm looking forward to the questions that might arise in the panel discussion. Thank you.
Thank you again very much, Anna. Thank you. So yes, so we have some questions for you all. So if the speakers can switch on their camera. So first of all, I want to thank you all for these presentations today during this interesting webinar. And I go ahead with some questions. I don't know who wants to address that, but let's start from the first one, which is quite technical. I mean, a little bit technical, and is asking exactly this question. What were the key technical challenges you faced testing your models with real-world data from the two use cases, the cities that you mentioned? I think that this is for Antonis. I don't know if you want to answer or also someone else want to answer. Let's go ahead. Antonis?
Yeah. The problem with stream data is that, first of all, it's not a predefined set, so we need to adapt that. And as we said, there were some variations in the density estimates specifically. So we will then do pretty heavy technical stuff. So the XGBoost inherently requires the presence of all observations in every single time we have to train it. So given the intricate patterns, let's say, of some city districts, it was unavailable for them to be trained using that model. So there was no other way to actually overtake this and cover for them, because either the accuracy would fail or the model would fail. So this was just a loss we had to accept, let's say, and try to find other ways to mitigate it through the regressor, for example, which was less specific. I don't know if that was a complete answer, let's say, but I tried my best to explain without delving too much.
Yeah, thank you. Yeah, I don't know if anyone else wants to add something, or we'll go to the second question. Thank you, Antonis. So the second question is more for the let's say on the side of the management of the urban mobility. So the question is, based on your tests in the Dutch cities, you mentioned during this webinar, these two cities, what improvements the municipality expect in urban mobility management through the implementation of these prediction models? I don't know who wants to answer, maybe Anna?
Thank you very much. What our partners are expecting here is, first of all, a model that they can trust. So there, the transparency is very important, so that when the model says, for example, in the next weekend, we are expecting a larger number of crowd to visit this specific region, why the model is saying that. And therefore, the explainability comes very important, because we can really point out that the model is looking at the value of the temperature, is looking at what is the likelihood of having rain, and we can ensure, at least on a daily basis, that we can provide the partners with the information of whether they should expect a risk, a categorized risk based on their threshold, and a large number of visitors might be expected.
Thank you, Anna. Anyone else wants to add something on this regard? I don't know. Otherwise, I go to the next one. Yeah, because we got another questions. And this is regarding the privacy aspect. So what are the main critical privacy vulnerabilities in mobility data collection, and how your solution addresses these risks while maintaining data utility for analysis? Who wants to address this?
I guess that should be me, right?
Yeah, I think, yeah, you're.
Thank you, Maria Letizia.
Yeah, thank you.
Okay, the main challenges that we face when ingesting mobility data with respect to privacy, of course, is the fact that, first of all, we need to understand which parts of these data points are risky, are capable of creating an environment where people can be de-anonymized, sorry. So the first part is the understanding of the potential privacy risks, and the second part is the sanitization process. So how we remove these risky records without actually destroying the data set, without making it unusable for other analytics processes. So the first part is basically related to the privacy attacks that we implement for the anonymization purposes specifically. So how specific and how we tune these attacks, because as you remember, during my presentation, we have thresholds for these attacks. So we can tune how lenient they are with respect to people that can be anonymized. If we make these attacks too lenient, then de-anonymization can be done by adversaries, but if we don't, then we might end up having to remove large parts of the dataset, which would be detrimental to the whole analytics workflow. So the answer is in the middle, I think, and it's important to find the best combinations for specific arguments and the variables, and very importantly, to understand the rationale behind the dataset and understand how important it is for each specific dataset to understand and to find out people's frequent locations and how you can map these frequent locations to specific de-anonymization patterns. So that's about it mainly, and of course the edge aspect is always there, because when you use the edge computing capabilities that might be available, it's easier for people to complete processes in situ, which means that again fewer risky data points can be found by adversaries, by potential adversaries. So I guess that's more or less it.
Great, thank you, George.
Thank you.
So, yeah, so I don't know if, I mean, we are nearly there. Is 3:20, so I don't know if any other speaker wants to add something, some final comment before closing. Yeah, of course, Yanis.
As I said in the introduction, we are now running the third year of the project. So these are mature results, but we expect even more in the months to come. So yes, I could say, as you usually say, let's be in contact with all people that join us today. I don't want, if you would like to give some hint about the follow-up webinar, the forthcoming webinar.
Yes, exactly. So in the next days, you can see on the website the next webinar, which will follow this one. So we are moving ahead very, very quickly and straight to the point. We want to address all this point. We want to bring ahead our work done in the Emeralds project. Also, I want to highlight that in the next week, we will be present at the event organized by AI, Data and Robotics in Brussels with our speaker that is here. She's here, Bahar will be in Brussels on the 18th and 19th of February. So if you are there or if you want to join the event, it is, the perfect occasion to be in contact with us. And also, I recommend you to subscribe to the newsletter and to follow us on the social media channels, because every day we have new stuff, new events. Now, we are in the final phase of the project, so we want to address this point. We want to achieve you as a community, which is already a great one. We want to reach more and more people ahead. So I want to also thank you all the speakers today, and wish you a great day ahead. And the appointment is for the next one. Thank you very much, everyone.
Thank you.
Thank you. Thank you all.
Thank you to the attendees.
Goodbye.